I'm really, really happy to be able to speak to you all today. And I'm going to be telling you about quantum algorithms, which is my area of research. And I work here at the University of Maryland. So it looks like Chris and I went for the same hook for our presentations. So I also wanted to mention that computers have been getting faster and better and smaller. We've been cramming more and more chips onto, into a single computer in the same amount of space. We can do more computation than we used to be able to do. And we've been just having exponential growth in this field in how fast our computers have been getting. But so Chris told you in the last talk that there's a limit to how fast and how small these computers can be because literally we're getting down to the size of atoms. And you'd need to be able to split atoms if you wanted to make your computers any smaller. But actually there's even another physical principle that tells you that this exponential growth cannot go on forever. If we wanted to have computers that were like the same size as they are today, but just had more and more and more calculating power, we'd have to cram so much information into such of a small space that actually the computer would turn into a black hole, literally. So you can physically calculate at what point your computer would turn into a black hole. So there are definite limits on how this curve cannot go on forever. Maybe even you could get around that splitting the atom problem, but I don't think you can get around the black hole problem. That just seems like we're not going to turn black holes into computers. Well, maybe you guys can figure out a way to do that. Right, so this curve cannot go on forever. There are definitely physical limits to how small we can make our computers. But the idea is that with quantum computers, and here this is one of the quantum simulators that's downstairs in Chris's lab, we can maybe just try a different path, and maybe we can get around this problem for at least a little while. Quantum computers are going to have the same issue. We can't build quantum computers super small forever. We're going to eventually turn them into black holes too, but hopefully with a quantum computer we can solve some problems that were previously unattainable with classical computers. And okay, I'm going to talk to you about quantum algorithms. Before I tell you kind of an outline for the talk, I just want to make sure that we're all on the same page with what an algorithm is. So an algorithm is just like a set of instructions that you give to a computer that tells your computer how to behave. So now when we have a quantum algorithm, this is just the set of instructions that you would give to your quantum computer that would tell the quantum computer how to behave. Okay, so in the rest of the talk, I basically just want to go over three main points with you. I first want to tell you about a couple quantum algorithms that we think are going to be both fast and useful. So these, in the first part, I'm going to tell you about two types of quantum algorithms that I think if we can build a quantum computer and if we can run these algorithms, they will really change the way our everyday lives work. In the second part, we'll talk a little bit about some of the things you heard from Chris, like superposition and coherence and interference, and why these things give you a quantum advantage and what's kind of going on inside the quantum computer. But then in the third part, I kind of want to talk about the limits of quantum computation. Quantum computers are not going to save the world. There are limits to what they can do, and I'd like to tell you what types of problems quantum computers are good at and what types of problems quantum computers are not good at. And of course, if you have questions at any time, please raise your hand, interrupt me. I'd be happy to answer them. Okay, so first I'm going to talk to you about the two types of problems that I think are going to be really transformative, the two types of algorithms. And they're these two things, factoring and quantum chemistry. Okay, so let's talk first about factoring. Factoring is the following problem. You're given a you're given some integer. Here this is a very, very large integer. And the problem is to figure out what two other integers multiply to the original integer that you're given. So if I tell you the original integer is 10, the two factors would be 2 and 5, because 2 times 5 equals 10. And you can, if I tell you 10, you can figure out 2 and 5 in your head, because we all know, hopefully, our multiplication table is up to 100. But if I give you this number and ask you what two numbers do you multiply to get to this number, this is a really hard problem, not just for us, but it turns out also for computers. Mm-hmm.
The two numbers you talked about, they always have to be primes?
For practical applications, they can be primes, but you could have, just factoring in general, it could be a more general problem. it turns out that this number is factored by 2 primes, and these are the 2 numbers.
I was going to say that.
Yeah, exactly. Are you a quantum computer? Okay, so yeah, so this is hard to do. I think it would be, well, okay, so it turns out it actually, not only, maybe you can't think about how to do this, but it turns out with regular computers, the computers that we use every day, we don't have a good way to solve this problem. So if we call this little d the number of digits, so the number I showed you on the previous slide had a couple hundred digits in it, the amount of time it takes for a regular computer to factor such a number is exponential. So it's exponential in the cube root of the number of digits. That's how much time it would take a regular computer to do this. So that's a very, very long time. We can't actually factor very large numbers, because if you add one more digit to your number, it scales up by a very large amount in time by how long it takes. On the other hand, if we had a quantum computer, we could do this in just d-cubed kind of scaling of time. So this is a huge, huge advantage for factoring. Okay, but I said that these are the types of problems that if we have a quantum computer that can solve these problems, they're going to be transformative. They're going to change the way our world works completely. And maybe you're thinking like, okay, I'm not spending most of my day trying to factor numbers, like why is this going to transform my world? But it turns out that factoring numbers are very important for our modern day e-commerce. So when you, say, try to buy something on Amazon and you put your credit card information into your computer and that gets sent over the internet, they're not just sending your raw credit card numbers. They get first encoded into some code so that people who are maybe trying to figure out your credit card information can't actually read it because they've been encoded. But the reason that they're safe, the reason people can't encode it, is because factoring is hard. So it turns out that if you could factor, then you could break the types of codes that we use every day. Literally, your computers are using these codes every time you buy something on the internet. If you could factor these numbers quickly, then you could break the codes. So once we have a quantum computer, almost all of our current crypto systems that we use today would be broken. We wouldn't be able to use them anymore. This is important for not only e-commerce, but also things like national security. I mean, not only we could actually break codes. Right now, because people think it's hard to decrypt these codes, the coded information is just all out there in the open. So once you can factor numbers, you can just go and learn all the secrets that have been sent out over the past while. So it will really transform things both from kind of a commercial perspective, and certainly the government is very interested in quantum computing for this reason. Yes?
Well, I don't know what those figures meant in the previous slide, but is that within a human lifetime that somebody could figure it out in the regular computing system, or is it?
No, they're so large. I mean, maybe it would take like 100 or 1,000 years to do one, decode one thing.
Waiting this out.
Yeah, it's not. I mean, maybe maybe in the old days, they started using these codes when computers used to be much worse than they are today. So maybe very old messages with our modern computers, maybe we can start to break some of them. I mean, that's not my area of expertise, but at least for current crypto systems, it would take many, 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 many years just to do one. And to get one credit card information is probably not worth 1,000 years of computational time. Okay, so this is one transformative technology. I guess we didn't get into this so much with Chris's talk with quantum communication, but it turns out that there are ways to create quantum crypto systems that would allow you to share information securely. So you could still, say, send your credit card information, but you would need quantum mechanics to do it securely. And people are also trying to create new codes that won't be susceptible to this type of attack. But in any case, because these types of codes are so prevalently used in our modern society, if we have a quantum computer, it will totally disrupt the way things work. The second kind of disruptive or really big application for quantum computers is in quantum chemistry. Okay, so the idea is if you want to simulate what happens between, say, the chemistry that happens between two molecules, maybe you're trying to see if they react with each other. if you wanted to try and simulate this with a classical computer, it turns out that's incredibly hard. So Chris was talking about like electronic states. And in an atom, it could either be, say, in a state 0 or 1. But if you have complex molecules and you're looking at their interaction, there are many, many, many electronic states. The electrons can be in all sorts of different configurations. And modern computers, the best supercomputers can only handle about 70 electronic states. So that's not very many states for the very best computers. But if you have a quantum computer, you can basically store each one of these electronic states using a single qubit, one of those single zeros, A0 plus B1 that Chris talked about. So this means instead of having a huge supercomputer that you need to simulate some kind of chemical reaction, you can do this with a very small quantum computer. In principle, with something that had, say, 100 qubits, could already start to simulate something that we can't do with the biggest supercomputer. I mean, I say about 1 qubit because we also need things like error correction, because things are always trying to look at our computer, right, and always trying to destroy those coherences and superpositions that Chris talked about. So we need more than just one. But in principle, with a very small quantum computer, we can simulate chemistry that we cannot simulate with the largest supercomputers. And there's so many applications for this. So we have quantum algorithms that do calculate some of the following things. So thermal rate constant, that's the rate of a chemical. Yeah.
When you're talking about modeling the states in a chemical reaction, would that be quantum analog computing or quantum digital computing?
People are trying both approaches. But I think, so actually especially for these solid state systems, people are considering analog approaches. But for these like thermal rate constants, it's more digital. Mm-hmm. Right, so the thermal rate constant is if you have two molecules and you put them together and you want to know are they going to react with each other and transform into something new, you might want to know, and you have the temperature that you have them in, you want to know how fast they're going to react. The thermal rate constant is the thing that tells you that. So we can calculate that just on a quantum computer. There are efficient algorithms. We can look at the energy structure of molecules to figure out, is that a hint? Oh, okay. Yeah. Okay, right, to figure out if just literally the energy of the different electronic levels of the atom.
My question was, does the process that quantum computer would be able to model, does it have to be quantum? Does the process itself have to be quantum? Could it be, say, protein interactions that have in multiple molecules? There is nothing quantum within interactions, but just there are a lot of possibilities that are too much for regular supercomputer.
That's a really good question.
Because that is something that's really valuable for modeling of protein interactions.
I think, well, so we're going to get, in the second part of the talk, we're going to talk about non-quantum interactions and non-quantum problems. So I think it depends a lot on what the structure of the problem is. Yeah, I'm not sure. So the final thing is simulating solid state systems. So you can actually have kind of like an analog computer. This is something that Chris does, where instead of having these qubits that are kind of digitally simulating things, you have something that is literally just trying to be the system that you want to understand. And so you can use these solid state simulators to study things like superconductivity and these weird materials called spin glasses and metamaterials. And okay, there are so many applications. I think there's so many ways that these types of algorithms could change our lives. I mean, if we think about drug development, right now, when people are trying to develop a drug, they have to go through the whole process of first building that drug and then testing that drug in the lab. And those two processes both take a long time. All of that could be done much faster on a quantum computer. You don't need to figure out how necessarily to combine how to make the drug. You can just kind of create it in your computer. It doesn't have to be real. And then you can test it in your computer. So just the lag time in creating things like new chemicals could be cut down by a lot by just simulating everything on a quantum computer, making sure that things work before you put on all the effort to try and create them, rather than first creating them and seeing if they work afterwards. There are the potential to build new technologies, so things like better batteries, even better regular computers. We can just simulate new semiconductor materials potentially on a quantum computer instead of trying to figure out how to build them first and then seeing if they work. Things like global warming. We would love to have a better way to capture carbon dioxide from the atmosphere. On a quantum computer, you could potentially test a whole bunch of molecules that might be good at capturing carbon and see which ones are the best before you invest a lot of time in actually creating them. Okay. So those were the two applications of quantum computers and quantum algorithms that will be the most transformative. Are there any, before I go on to the second part of the talk, are there any questions?
Any examples of, not examples, show how an algorithm works, even a trivial one? I'm having trouble wrapping my mind around how I would write an algorithm.
If you're not, I'm currently typing an email that has a link to Scott Aaronson.
Oh yeah, I have that at the end of my talk too.
I'm emailing.
So in the next section, I'm going to kind of try to give you a rough outline, a rough idea of what it's like for me when I try and write algorithms. I don't know, I'm not going to write down like the mathematical steps that are involved, but yeah, unfortunately not for this talk. Yeah.
Is there a timeline for the development of computers that can do these things, like in our lifetime or in 5 years?
That's a good question, and it's really hard to know. I would say actually in the past couple of years, it seems like we've made a lot of progress. But still somehow quantum computers always seem to be 20 years out. At the same time, I think we are getting very close to these quantum computers that are maybe 100 or 1,000 qubits. And that would, some of these very simple quantum chemistry problems, you could now start to do. And especially some of this quantum simulation of solid state systems you can start to do. But like factoring, for example, I think we're still a long ways from being able to factor any number that we can't already do with a regular computer. But when Chris comes back in the discussion, you should ask him, because he's actually trying to build a quantum computer. Okay, so I'd like to tell you a bit about what it's like to try and design a quantum algorithm and what it is about quantum computers that give us a speed up, like what makes them different from a regular computer. And a lot of this is very similar to what Chris told you about before. But I'd like to give you my metaphor. When I think about kind of what's going on in a quantum computer, I have this metaphor that I often think of. And okay, it's not the simplest metaphor, but quantum mechanics is not that simple either. So I hope you'll bear with me. But my metaphor for a quantum computer is that it's like a coastline, okay? And here we have this, I think, a really beautiful picture of some coastline. And what we see is we have waves coming in from offshore. And those waves are kind of interacting with each other. There are some islands right off the coast, and those islands are shaping the way the waves interact. And then eventually the waves are hitting the beach. But because of the kind of shape of the coastline and because of these islands that are placed in different areas, in some places you're getting a lot of waves, and in some places you're getting almost no waves. So for me, this is very similar to what a quantum computer is doing. There's kind of waves that are interacting with each other, and then eventually we get kind of waves at the end. And these kind of waves crashing on the beach are like the output of the algorithm. And now, for me, the output of the algorithm is good if there's kind of one large wave in one place. Like Chris was saying, you kind of don't want everything to be spread out. You want to have one large wave in one place. And the place where that wave occurs, that'll be kind of the output of your algorithm. And so what is my job? I'm trying to engineer this system. I want this system to give me something useful at the end. And what I can do is I can manipulate how these waves behave. So for me, writing an algorithm is somehow like someone gives me a whole bunch of boulders, and now I can place these boulders wherever I want along the coastline. But somehow I want to place these boulders in such a way that they will cause these waves to interact in such a way that at the end of the day, there's just one large wave at one location, and somehow that is going to give me the answer to my problem that I'm looking at. So at the end of the day, we want something like this, like one huge wave, and nothing, there's no other waves around. There's just this one giant wave. And maybe this seems like, well, how on earth do you know where to put those boulders. Like, it seems impossible. And I have to tell you, for me, it's not always clear either. Like, a lot of what I do is kind of just intuitive from having studied what people have done in the past and seen what works. A lot of times I just have to throw boulders down and like see if it works. And a lot of times it doesn't. So it's not like, with a regular computer, algorithms I think are pretty straightforward. Like, it's just you do A first and then you do B second. Like, if I told you to write instructions for how to make a peanut butter and jelly sandwich, I think you could all do that. But this is a very different experience. Like, to me, it's totally different. And it's not an easy thing to do. It just takes a lot of practice, and eventually things start to happen, and you start to see waves. Yeah?
In that metaphor, there's a lot you can't observe because it's under the water. Is that also true for what you're trying to accomplish, that there's a lot that's just not visible to you or not known?
Maybe not.
In terms of where to put the boulders, like, are there just locations you can't see?
Well, it's just, I mean, it's kind of like there's just so much going on that you can't always calculate what's, it's hard to know. When you put a boulder here, that has such a large effect because there's so much water hitting that boulder, and it's very complicated that it's hard to predict what the outcome of that, putting a boulder in one location or another will be. And I mean, yeah. So similar to that.
You can't see where the boulder is in your metaphor. It's not exactly the right.
Yeah,
It's
yeah.
not invisible to you.
No, I don't think, yeah, it's not invisible.
Really complicated.
It's just really complicated, yeah. Okay, but so I wanted to use this metaphor not just to give you a sense of what it's like to design quantum algorithms, but also to give you a sense of why quantum computers are powerful, like why they have a speed up compared to regular computers. So basically, I think, in my opinion, well, in my view, there are basically two things that give a quantum computer its power, and Chris kind of touched on these two things, but I'd like to use the metaphor to kind of explain them. So the one thing is superposition, and so Chris talked about this a lot, that the cat can be both alive and dead at the same time. Okay, but so what does this mean in terms of our example here of the coastline? The water somehow it's not just coming all from one place. It's not just taking one path. The water is somehow, whether there are waves or not, doesn't just depend on whether you have a rock in one location, right? It depends on all of the rocks all over the coastline, because somehow the waves are exploring the full space. So for example, if we want to figure out if there's a wave that occurs at this location, water that hits this location is coming from all these different parts, right? There's not just water here. The water that ends up here has not just followed a straight line. So somehow the system explores many possible paths in order to get to one output. And this is like the idea of superposition. But superposition is not enough. It's not just that it explores all the paths. It's also, the second part that, again, Chris touched on is interference. And so interference is something that happens just classically. If we have two waves and they're both kind of have peaks, and when we bring those two waves together, we get a new wave with a bigger peak. And that's called constructive interference. But if we have one wave that has a trough and one wave that has a peak, and they come together, they kind of cancel each other out, and you get destructive interference. So the art of designing a quantum algorithm is to recognize that you have superposition. You have all these paths coming in. But some of these paths have waves that are peaking right at that point in the beach. And some of these waves are troughing right at that point. Right? So they might cancel each other out. And so the art is to somehow get all these paths to peak at the answer and kind of cancel each other out everywhere else. I mean, that's the most, I don't know. That's what it feels like when you're trying to design a quantum algorithm. Yeah.
It almost seems like you have to start with the answer, which seems very backwards to regular computer programming. You know what your answer.
Well, you don't.
Well, when you don't know what your answer is, well, you wouldn't need to do it, but you sort of have to know what sort of answer you're looking for.
Yeah. I mean, well, at the end of the day, you have a wave somewhere or you don't, and you don't know. Yeah, I'm not sure. Maybe I'm not understanding.
Maybe I'm putting it badly on the right of
Well, maybe we can discuss more later. Other questions about this before we talk a bit more about more specific quantum algorithms, I guess? Okay, so I told you, at the beginning I told you about these kind of fantastic quantum algorithms that I think are going to transform our world, but I don't want you to get the feeling that if we throw a quantum computer at every problem, it's going to just be able to solve every problem. So we're going to talk about when we can actually prove whether we get an advantage from a quantum computer or not. So before we had this factoring algorithm, right? And we saw that there was a huge speed up from what a quantum computer can do versus what a regular classical computer can do. But the thing is, we haven't actually proved that the quantum computer is better. Mm-hmm.
Use Euler's number, right?
Yes.
So I was doing some calculations here when you said that, and I was a little confused. It's 2.71 something to say a cube root of say 5 digits long. Okay, cube root of 5 digits is 5 is 2 point something. So either
Yeah, so it's not that large.
So it just seems like the curve doesn't fit the difficulty. Whereas dq is
If you go out to at 5, you're not going to see it. If you went out to 100, yeah, you start to see a really big difference when you get further out. If you get to 100, 1,000. That's a good question. I can probably, calculate that and let you know. Yeah, I'm not sure exactly where. And these those tildes mean that there are some constants out in front too that I'm ignoring. So those constants will affect where they cross to. Mm-hmm.
You need to get to just one answer for some problem.
Yeah.
But just having one answer come out seems insufficient if you didn't consciously design an algorithm that you know leads in the right place.
Yeah, exactly. Yeah, so you can always have one answer come out.
That's not just getting one wave, but getting one wave in the right place.
Can I talk about it? Sorry. I mean, that's the whole challenge. I mean, you need to figure out how to design things so that you not only just get one wave output, but in the correct place too.
Which means you have to have an algorithm. Where's the algorithm coming from?
I guess in the metaphor, it came from where I placed the boulders, right? So
Right, but how
that
do you know
that
where to
encode.
place the boulders?
Well, so using mathematical analysis, I mean, you can see whether the operations will ultimately end with you having the correct state.
Like a lot of these things, it's hard to factor those giant numbers that you put up earlier. But once you have something that's probably a factor of one of it, dividing the big number by the maybe a factor and seeing if it works, it's tricky. You do that immediately. So you can set up these algorithms that it's hard to know what's going to get you the right answer, and sort of play around with it and try things. But finding out that you have the right answer is really easy a lot of times for these problems. So that's the validation that you can do with this. Is frequently you're trying to solve something really hard, but checking that you've solved the really hard thing is very easy. And so that's the step that you get. So you don't have to know what the right answer is in advance. You can verify that you got the right answer from your procedure without knowing what it was to start.
More on this in that reference you sent out.
Probably.
Yeah, right. It turns out it's much easier to multiply two numbers than it is to factor. So once you've, say, solved the factoring problem and you have those two factors, you can check that, you can multiply them back together very quickly and check. And so, quantum computers are probabilistic, so a lot of the times, like maybe 1/3 of the time, they do just output junk. But as long as 2/3 of the time they output the correct answer and then you can check it, that's okay. And maybe this answers your question a bit too.
Also, you could run the algorithm more than one time and look at when it comes out with the same answer, and that's probably the answer you're looking for.
Yes, exactly. So often any quantum algorithm, you would not just run it once. You would run it many, many times and see that you get the same answer coming out. Yeah.
Yeah, that does actually help.
Okay, great. Okay, so I told you that there's the separation between the best thing we can do with a regular computer and the best thing we can do with a quantum computer. But it it turns out we don't know that there's not a better way to factor numbers on a regular computer. This is just the best that some guy has, I think it is a guy, has come up with. But that might just be a lack of our creativity as like humans. Like I just heard someone say yesterday that an expert in math who studies these types of problems thinks that there probably is an algorithm to factor numbers that scales more like d cubed that you could run on a regular computer, but that humans will probably never have the capacity to figure it out. Basically, there could be a better algorithm. We have no proof that there's not a better way to do this on a regular computer. All we know is that the best we have with a regular computer is much worse than the best we have with a quantum computer. But for me, what I really like to do is actually prove things. I would really love to show that there are problems where you do a lot better if you had a quantum computer than a classical computer, and really prove that once and for all, and not just have this amorphous, well, maybe there could be a better algorithm, and we just are too uncreative to figure it out. But so to do that, we have to look at a new type of model, and this model a new model of computing, and this model of computing involves functions. So hopefully you're all familiar with quadratic functions like this guy. So this is just an explicit description of a function. If I give you this and I told you x, you could calculate f of x, right? You would just plug it into the right-hand side and do a little bit of algebra, and you'd be able to find the answer. But we can also think about a black box description of a function. So instead of having an explicit description, instead I'm going to give you a box that somehow stores that function inside of it. But you don't know what it is. You don't have this explicit description. But you can still find out about what the function's doing by asking it questions, which we call queries. So here, this box is actually hiding exactly the same function that we had before. And so you can ask it, what is the value of the function if I plugged in x equals 0? And it would tell you it's -3. Or what's the value if it equals 1? And it would tell you it's -1. OK, so now with this black box type of description, we can look at a new class of problems. So the problem is someone gives you a black box that hides some function, and now they want to know, does that function have some property? I'm going to give you an example in the next slide, so if this is seeming a little vague. But basically, we want to figure out something about the function, and we want to do that using this mysterious black box as few times as possible. So let's look at an example. Suppose I give you one of these boxes, and I promise you that the thing inside the box, it's either quadratic, so it has this form, or it's linear, so it has this form. OK, so my question to you is, how many times do you have to use this box to figure out which is the case?
3 times?
Twice? 3 times? Those are both very good at answers.
Box is the one that you ask questions of?
You ask questions of. And you want to figure out if you're in the quadratic, you're promised it's one of these 2 cases. You want to figure out which case you're in. OK, so the correct answer is 3. So let's look here. Suppose you ask the box 3 questions, like 0, 1, and 3, and you get 3 answers. Now you can plot those 3 points on like a graph here. And now you just want to know, is there a line that goes through those 3 points? And you can see that there's, in this case, there's not. It's a parabola is the thing that fits. But with just 2, if you only took 2, you could fit either a parabola or a line to it. But with 3, you can check. Either it's a parabola or it's a line. But the thing that is important here is that we only count the number of times we use the box. Like actually, if I was running this on a computer, I would need to have some kind of algorithm that created a line and checked if the line went through the points. And that would cost some computing time. But in this model, we don't worry about that computing time. We just think about this box and how many, somehow this box, you have to pay $100 every time you use the box. And so your goal is to be as cheap as possible and solve this problem while using the box as few times as possible. And this is, let's see, maybe I will just, this is actually kind of a good model. Suppose you're trying to predict the weather, right? To run weather predictions, those are really extremely costly. To do one weather prediction, you have to take in all this data and all this information, and it probably takes an hour to do one simulation. And now if I'm the weatherman and I want to figure out what the weather is tomorrow, I want to run this simulation as few times as possible. At the end of the day, I only want to figure out what's the temperature going to be tomorrow. I only need like one piece of information. But I'm going to have to run this huge simulation. Like that's going to be my main cost. So I want to figure out how to get the property of the function out while kind of running this function as few times as possible. So even though in the real world we don't literally have black boxes, we have things like very complicated functions that are very hard to evaluate, like calculating the weather. Okay, before we move, now we're going to go quantum. So before I do that, are there questions about this model?
If you go quantum with the weather predictions, are they going to get better?
I do not know. They could be. That I don't know.
The act of interacting with a quantum system will improve the weather.
Right. I mean, it could be like NASA is interested in quantum computers, and I think they're interested in when they can shoot off rockets if the weather's going to be good. I mean, to me, it's unclear that there will be a good quantum algorithm for weather prediction, but you never know. Okay, so now we can have the same problem, but we're just going to make it quantum. So what I mean by that, the function could be exactly the same. The function inside the black box could be the same, quadratic or linear function. The only thing that's going to be different is that instead of asking it a question that's just like classical bits, we now ask it one of these, we can just ask the question with a quantum state. And then also the output of the box is also going to be a quantum state. So actually all this box is one of these transformations that Chris was talking about. It's something that can like flip the state of the system depending on the value of the function. Okay, so the idea is now we can ask the same question. Say you have some function that's hidden inside the box, and you want to learn some property like what's the temperature going to be tomorrow. But now you can use this box inside a quantum computer. And again, we still want to use the box as few times as possible. And right, so we call quantum query complexity the number of times you use the box. And okay, the thing that's really fantastic that I love about this model is that we can actually put bounds. We can really prove advantages of quantum mechanics in this model. So we can really prove, like once and for all, a classical computer cannot solve this problem without using the box a certain number of times, whereas a quantum computer can solve the problem using the box many fewer times. So this is what I like so much about this model. But also I think it'll give us some insight into quantum algorithms in general. And again, just like in the classical case, we're ignoring maybe the rest of the computation takes a lot of time, but we're just only counting the number of times we have to use this special box. Are people still with me? Okay, we're going to look at some examples now. Okay, so here is a function. Here I've given you an explicit description of the function, right? I've told you the inputs, x can be 1, 2, 3, 4, 5, or 6, and I've told you all the outputs. But if in the case that we're considering, you would really be given a black box version. So you wouldn't know what all the outputs are, but you could ask the box a bunch of questions, and you could learn what they all are. And we call this a Boolean function because the output is only a 0 or a 1. And also, I call this little n the number of inputs. So little n tells you the size of the function. Okay, so what's a property of this function that we might want to learn using it in terms of a black box? So one thing we might ask is the number of ones here even or odd? So the output of the function is a bunch of zeros and ones. We can count up the number of ones, and we can say, is that divisible by 2 or not? So in this case, we see that there are 3 ones. That is not divisible by 2, so it has odd parity. So this is just a property of the function, right? So you might ask, well, how many times do you need to use the black box in order to figure out that parity? And so what you can prove is that you get almost no quantum advantage for this problem. The classical number of black box uses you have to use is n. You basically have to look at everything, every single input. And the number of quantum black box uses you have to use is n over 2. So you get a factor of 2 speed up. So this is like nothing, right? Like, okay, so suppose you can solve this problem in 10 minutes on your quantum computer. Well, you could solve it in 20 minutes using a regular computer, and I don't think that's worth spending billions of dollars trying to build a quantum computer for. So I really wanted to show you this to show you that we can really prove that there are some problems that that all this specialness of quantum mechanics and quantum computing doesn't buy you anything. And really, it's only very specific problems where you do get an advantage. And we'll talk about why you might get that advantage. Yeah?
Can you explain why it's n/2?
Well, so it turns out if you just had, suppose this were, instead of having n equals 6, if it was just only 1 and 2, if there were only 2 inputs to the function, it turns out that with one quantum query, you could figure out the parity. And so then basically you just divide the function into, you just look at the first 2, then look at the second 2, and that's the best you can do. And you can do that because basically you can create a superposition of the 2 and figure it out. Yeah. Mm-hmm.
I imagine like the paper was very technical, but isn't it possible that there was another way to do it that could reduce the steps even further, or no?
No, that's what's that's what I love about this model. You can prove absolutely there's no better way to do it. Yeah, this is the best you can do in either case. Yeah, it's kind of surprising. Okay, so let's look at another example. Okay, so here we'll stick with Boolean functions. And again, just the outputs again are just 0 or 1. And now the question that we want to know is, are there any 1s? Does the output contain any 1s, or is it only all 0s? So obviously in this case there are 3 1s, so we see that, okay, yes, there are 1s. And this problem is basically the problem of search. Imagine that they're mostly 0s and there are only a couple 1s. You're trying to search for those inputs that have value 1. But this is a black box. Like, how are you supposed to find where those guys are, right? You don't have this explicit description, so you don't know where to look. So you're just kind of searching around blindly for those inputs that have value 1. And so in this case, we can compare how a quantum computer does and how a classical computer does. Again, a classical computer has to use the box like the full n times. But a quantum computer now, it does do a little bit better. It gets a square root speedup. So if you could find that item with 10 minutes on a quantum computer, it would take something like 100 minutes on your regular computer. So we're starting to see a little bit more of a speedup, but still, square root, it might still not be worth investing $1 billion for a square root speedup. I don't know. Okay, but so where were these speedups? I thought quantum computers were so great. But it turns out we have to look at different types of problems to get quantum speedups. So let's look at a new type of function. In this type of function, it's no longer Boolean. So this means we can have different integers at the output. But notice about this function, it's periodic. So we have 0, 4, 3, 0, 4, 3. Okay? And now, suppose I give you a black box. I promise you that it's periodic like this. It's repeating after some number of steps. But I don't tell you when it's repeating. And my question to you is, how many steps before it repeats? That's the thing you want to try and find out. Okay? So now we suddenly see a huge quantum advantage. It turns out that with just a single black box use of this box in the quantum setting, you can figure out this problem with high probability. Okay. It's a probabilistic process, but with high probability, with one quantum query, you can figure out the period of that function. Whereas on the other hand, if you had this classical box, it would scale like little n. So this is a huge, huge quantum advantage because you can have as large of a function as you want, and the quantum query complexity doesn't change. The classical just gets bigger and bigger and bigger and bigger and bigger. So suddenly we see for this type of problem, we have a very large quantum advantage. Was that a question or a stretch?
No,
Okay. Okay. And let's look at one more example where we get a big quantum speedup. Okay, this is called the hidden shift problem. And again, all of this is, we can actually prove this is the best you can do classically, right? There's no way you can do better than this. So we can prove this is a quantum advantage. Okay, for this hidden shift problem, now we're promised that you have, this is G you're given explicitly. So you can look at G. You see what all of its outputs are. F is the black box function as before. And now what you're promised is that X is just F is just G shifted. So if we look here, let's see. Right, so here 1 goes to 3, 2 goes to 1. But down here, if we look, here 5 goes to 3, 6 goes to 1. These two functions are just kind of shifted from each other in x. So like they're basically the same function. They have the same shape if you drew them out, except just kind of shifted from one another. And then the question is just, what is that shift? Okay, so you know G, you want to find what the shift is with x. And again, here we have a quite considerable quantum speedup. Not quite as extreme as before, but still this is an exponential speedup between the number of uses of the black box, quantumly and classically. And again, this is something we can prove. Okay, so I mean, I wanted to show you these examples to give you a little bit of a sense for when you can see a quantum speedup and when you can't. So let's kind of look at these 4 examples and think about what it might be about these examples that in some cases allowed you to get this big quantum speedup, but in other cases, like, there was a very small speedup. Okay, so one thing you might have noticed was that, I didn't really emphasize this so much, but in the case where we had a very small quantum speedup, there was basically no promise, which means that the value of the function, these zeros and ones, it could have been any possible sequence of zeros and ones. On the other hand, when we saw that there was a large quantum speedup, there was a promise. Like we were promised it was periodic, right? Or we were promised that it was the same as G, but just shifted. Okay? So that's one thing we saw. Another thing you might have noticed, this is pretty subtle, and this kind of gets at the heart of this model, is that the outcome of the property depends, in the case of small speedups, depends on only one value of the function. So what do I mean by that? Let's look at this function. Here we have f being all zeros. Okay, and so in this case, this function has, in the case of search, there are no ones, and in the case of parity, it's even. But now if I were to change any single one of these zeros to a 1, that would flip the value of both properties, right? I would go from having all zeros, and now suddenly there would be a 1. So just changing one of these bits, and I can change one of those bits anywhere in the function, I change the property. So this property is somehow very sensitive to every single piece of information that the function has. And so it seems like when something has that property, quantum computers don't seem to have a very big advantage. On the other hand, for these types of functions, if you wanted to change the period, you couldn't just change one value of the function. You would have to change a global property. You'd have to change the function in many places in order to get to a new value of the property. And so when we get back to our metaphor about thinking about why quantum computers work, remember we had this waves that are exploring the full space, but somehow we need things to add up coherently at the end of the day. And if the problem doesn't have a lot of structure, if every single little piece of the function is important, then it takes a long time for things to add up large enough to be a signal. But if the function already has all the structure built in, the waves can kind of explore that structure and you get a really big coherence like immediately. So when you're thinking about what problems might give you a speed up, like your protein question, I don't know, it depends a lot on the structure. And maybe they have nice structure and maybe they don't. Okay, so if you'd like to go deeper and really understand a little bit more about how these quantum computers work, I think this is what Chad just sent out, I would highly recommend this blog post. It's not mathematical, but it does go a little bit deeper than I have into like the details of quantum algorithms, but I think the approach is somewhat similar to kind of how I've described it. He talks about interference and superposition in using a different metaphor. I believe he used clocks on a wall. So if you'd like a different metaphor than waves at the ocean, this might be good. And that's all I wanted to tell you about, but I guess Chris and I will be around and we can hopefully discuss more of these questions.